We now look at a different sorting algorithm. This is known as a distribution sort. The reason we look at a different algorithm is that this algorithm will later be generalized to solve more complicated computational geometry problems. The sorting algorithm we saw previously is a generalization of a merge sort, where instead of merging two lists at a time, we merge a bunch of elements, a bunch of lists at a time. In this algorithm, we are generalizing quicksort. If you remember quicksort, in that algorithm, we have one pivot, and then we partition the input into two sides, the side that is smaller than the pivot and the side that is larger than the pivot, and then we recurse on each side. In this multi-way quicksort, what we do here, instead of splitting into two arrays, we split into multiple arrays. In particular, we use M over B splitting elements, or M over B pivots, and then we distribute the input elements according to these pivots. Basically, the way this works is that we assume that we have a bunch of pivots that are evenly distributed in the rank space. In other words, if this is my sorted element, I assume that my pivots are essentially evenly distributed in the rank space. So these are my pivot elements. I will get back how to compute them, but for now, assume that they are given, or I can compute them somehow using a procedure. Right, so this is pivot 1 up to M, more or less, where M is M over B. Okay. Then what we do here is that we look at the input. So this is the input, and we partition this input using these pivots into a bunch of lists. So I will get a list that is smaller than the P1. I will get a list that is between P1 and P2, and so on. Okay. How can I do this? As I claimed, we're going to do it in the exercise classes. I could do this if the number of pivots is M over B. I could do this operation in O of N over B IOs. So in O of N over B IOs, I split my input into small m number of lists, and the size of each list goes down by a factor m, because I assume that these pivots are evenly distributed. So in other words, the gap between every pivot is roughly n over m. Then this process continues until we reach lists that can fit inside memory. Once the list size is m, then I could just sort it inside internal memory with no problem. If you look at how many IOs this takes, I have this many phases, or log m over b of n over m phases. And the reason behind this is that this number here is how much the size of the lists go down, right? So the size of each list goes down by a factor m over b at each step. And this is when I stop, right? Oh, sorry, or in other words, oops, hello. This is, the m is when I stop. When the size of the list goes down to m, I stop with my recursion. So therefore, my stopping time is like this. Okay, in the rest of the video, once I can get my annotation tools back, I'm going to talk about how the splitting elements is done. But before doing that, I'm going to remind you how the linear time splitting works in the internal memory. If you remember how linear time splitting works, you can just skip this phase. But otherwise, just listen along. Because the algorithm that we're going to use to find M over B splitting elements is a generalization of the algorithm, or linear time selection algorithm, that we know from internal memory. So the selection algorithm, if you remember from the algorithm and data structure course, is basically finds the ith element in the sorted order. So the procedure works like this. We first group the elements into arbitrary groups of size 5. So I have n elements as my input, and I group them into 5 elements. So there are 5 elements in the first group, 5 elements in the second group, 5 elements in the third group, and etc. Okay? This grouping is arbitrary, so you can just take the first 5 elements in the array to be the first group, and etc. So basically, you don't need to do any operations for step 1. Then you compute the median of every group. So let's say this is the median of every group, and let's assume that these 2 elements are smaller than this median, and these 2 elements in the group are larger. So for every group, we find a median, and we find which 2 elements are larger than the median of that group and which elements are smaller, and so on. And finally, once we find the medians, we recurse on the medians. We find the median of all these n/5 medians that I computed. Let's do it like this. So I look at all these medians. There are n/5 of them because that's how many groups I have, and I found one median among them. Okay, let's say that this black element M is the median of the medians. Okay, what can I conclude? Well, we can make some very interesting observations. If I look at any element, so this element is smaller than the median, but these elements that are smaller than the median in the group are also smaller than the median. So basically what I can conclude is that all these guys are smaller than the median itself. Smaller than value M, and all these guys up here are larger than M. Because if you look at, for example, this group, this median is larger than M, and these two elements are larger than this median. So therefore, all of these elements are larger, all of these elements are smaller. How many elements are inside each group? There are roughly n/10 groups here, right? Because I had n/5 groups and I found the median of the medians. And there are 3 elements per each group. So therefore, the number of elements here is 3, 10 of n. Similarly, I have 30% of the elements. So 30% of the elements over here, 30% over here. Then I split this array, the input array, using M. Okay, so let me erase everything. So I look at the array and I split it into 2 chunks. A chunk that is smaller than M and a chunk that is larger than M. Based on what we have shown so far, there is at least 30% of n over here and at least 30% of n over here. Of course, one of them is going to be larger, but there is at least a 30% of them. Then we recurse. We recursively find the rank I in each one of them. For example, if I know there are, let's say, x elements over here, then if I is bigger than x, then I need to recurse on this side, and I need to find an element that has rank, I guess, I minus x plus 1, okay, and so on. If you look at the recursion for this, the first step takes O of n, let's say capital N. The second step takes let's try this again. The first step takes O of n time. The recursion is over n/5 elements, so this takes n/5. This takes O of n time, distribute the two lists according use the computed median, and then recursion. This recursion will be recursing into a list that has at most 7/10 n. Right? At most 70% of the elements will be inside the list that I will be recursing on. So therefore, this is going to be f of 7/10 times n. Okay. And now the interesting thing is that when you add up this, it's going to be f of n equals f of 710n plus f of, and 1/5, I could write it 210n plus O of n. This is a slightly complicated recursion, but basically speaking, 7/10n, 70% plus 20% is like 90%. So therefore, I'm roughly recursing on 90% of the elements. So therefore, I have a geometric series. So therefore, this recursion solves to O of n. So that's how the internal memory selection algorithm works. It's a linear time algorithm that's basically work like this. And then in the next video, we're going to show how this can be generalized to IO model.